my slides?
Yes, well.
Okay, good. Well, first, thank you for having me here. So I'm Aubin Archambault from the physics lab of INS de Lyon in France, where I defended my PhD under supervision of Caroline Cross-Thibierge, Ludovic Bellon, and Sergio Ciliberto. So I will show you a bit of the work that I did during my PhD on the bound that we can obtain for the amount of work that one can extract on information engines. So if I can change my slide, yes. So the question is how much work is available when one builds an engine or from a transformation. So in stochastic thermodynamics, we have the very famous Jarzynski equality that links the amount of work that one exchange with the system during transformation with the amount of with the free energy change in the system, delta F. And by using the properties of the exponential function, you recover this bound on the average work that one can extract, which is equivalent to the second law of thermodynamics. And this bound is basically that you cannot, on average, extract more work than the energy change that happened in the system. However, this bound breaks in the case of feedback protocols. So protocols that are adapted to the result of a measurement performed on the system. There has been some extension to cover this scenario, and the first one is by Sagawa and Ueda in a paper from 2010, in which they derive a Jarzynski-like equality, where the information taken from the measurement allows for work extraction. So they show this Jarzynski-like equality with I's information from the measurement. And by using the same trick with properties of exponential function, you see that the information behaves naturally as something that allows you to extract work. The more information you extract in your protocol, the more room you have to extract work during your process. However, this does not take into account the specificity of the protocol you've chosen. And definitely for a given measure, for fixed measurement, I can do many different protocols, and some have to be better than others. And there must be a way to take that into account. And this is a refinement that was proposed by Ashida and coworkers in 2014, where they introduce a new term, IU, that is the amount of information that is not used by the protocol. And once again, they're able to derive a Jarzynski-like equality, which results in a tighter bound on the amount of work that one can extract, where your amount of work that one can extract on average is bounded by the energy change in the system and both the information that you measure minus the amount of information that was not used. So this is a bound that we wanted to test experimentally. And to study the stochastic thermodynamics experimentally, the system we used are micro cantilevers, so they are clamped beams with dimension typically on the micrometer scale, and with deflection driven by the thermal noise. So this deflection X behaves as the position of the 1D underdamped Brownian particle in an harmonic trap, with typical frequencies around 1 kilohertz and quality factors around 8. And the trick that we used is that thanks to fast electronics, we were able to build a feedback loop where the system is driven using an electrostatic force. And the point is that our electronics have a response time that is 1/1000th of the typical time scale of our oscillator. So this gives us a system that behaves as a 1D underdamped Brownian particle submitted to both the thermal noise and an arbitrary tunable force that allows us to perform a lot of different feedbacks. So the protocol we wanted to test is the one that was proposed by Sagawa and Ueda in this paper from 2010, which is quite simple. You start with your particle in a single potential well centered in -L at equilibrium, and you perform a measurement. If the particle is on the positive side, it means that it is in a high energy state. So by switching your potential instantaneously from -L to a center in +L, you can extract work from the system. If, however, after your measurement, the particle is on the left side of the potential well, it means the particle is in a low energy state. So you choose to do nothing and no work is exchanged. At the end, your particle lies in a single potential harmonic well, and you can wait for equilibrium and perform a new cycle. So we implemented this protocol in our setup, and we measured the probability distribution of the work exchanged for each realization of a cycle. So these are the blue crosses that you can see here. So the key point here is that all the work lies in the positive side, which means that we are extracting work with a strong peak in 0 that corresponds to all the events where my particle was on the left side and I choose not to switch the potential. So the work exchanged is 0. Since everything happens from an equilibrium distribution, it's easy to compute the probability distribution that you expect for the work, and you see that the green theoretical curves matches perfectly our experimental data. So the conclusion here is that we build an engine where from a single thermal bath using information as a fuel. I have one parameter in my experiment, which is L, which controls the spacing between my two potential wells. And by tuning this parameter, I can optimize the amount of work that I extract from my system, once again, in very good agreement with the theoretical prediction. Now the question is, how does it compare to this information bound that was proposed by Shida and coworkers? What can we say about information? So in my protocol, since I'm performing cycle, the energy change delta F will be 0. So everything is driven by the delta I, which is the amount of information minus the unused information, and I will compute both of these terms separately. Here it will be quite easy because my protocol involves a single measurement, so there are no correlation between measurements, and my system always starts from equilibrium, so we know the probability distribution quite well. So to compute the amount of information, since I'm just measuring the position of a particle at equilibrium, I can take the Gibbs distribution, and the information is given by the Shannon entropy of this distribution. So for a measurement x, I have an amount of information minus log of p of x, which gives an average information 1/2 plus log of square root of 2 pi. And here you see that there are no dependency on the protocol, so L is not a relevant parameter for computing the information. Now for the unused information, we need to study the backward protocol. It's something that is linked to Crookes' theorem. So we need to study the time reversal of our trajectories. So when I perform the forward protocol, I have first a measurement, then my protocols are different. When I perform a backward protocol, my protocols are first different, and then there is a measurement. So due to causality, I cannot perform a feedback anymore in the backward protocol. We need to choose a protocol beforehand and see how the outcome of the measurement compares to the protocol that we choose. So when we do that, many things can happen. You have a lot of different trajectories here, but as you can see, some of them only exist in the forward protocol due to the feedback. Some trajectories are eliminated in the forward protocol by the feedback and only exist in the backward process. Such a trajectory, for example, would be trajectories where my particle is in a low energy state, but my potential is switched. And these are scenarios where if I do that, I would be losing work. So these trajectories that exist only in the backward protocol are called singular trajectories. And the definition that is proposed for the unused information is to take the log of the probability when one chooses a fixed protocol to get a measurement that is coherent with this protocol in the context of the feedback when you perform the reverse protocol. It translates basically to measuring the probability in the reverse protocol of non-singular trajectories. For our protocol, which is quite simple, you can compute this average amount of unused information. And here you see that it catches the dependence on the protocol since L, my only parameter, appears here. So now I can put both the information and the unused information together and compare it to the work. So here it's as a function of L, the information, the unused information in green, and delta I in red compared to the experimental average work that I can extract in blue. So as you can see, the information does not depend on L. The dependence on the protocol is caught by the unused information. And when I compute the delta I, it's a very tight bound to the extracted work, while the information alone would be a bound, but a very loose one. So now what does it mean to have such a discrepancy between the two bounds? It means that I'm taking a lot of information, but actually I'm using only a small part of this information to extract work. This can be understood as the fact that I have a very precise measurement of the position of my particle, but then I choose to perform only a binary protocol, which does not require a lot of information.
Just a reminder that we just have entered the question time.
I'm finishing. It's perfect. So yeah. So to conclude, we have shown that this bound is indeed a very tight bound on the extracted work, and the fact that most of in this protocol most of the information is unused. So there must be a way to find a protocol that is more clever than this one. And there are more other questions for me. Can we find a protocol with a very low amount of unused information? How low can it be? Can it be 0? And experimentally, I have an underdamped system, so maybe I can build more complex feedbacks, for example, with the velocity. With that, I thank you for your attention. If you have any, you can contact me by mail if you are interested, and you can find a lot more detail in my manuscript that is available online. Thank you for your attention.